Okay, chapter two, the environment, chemistry, energy to life. And you guys have done chemistry a long time. And so this one should go fairly quickly. We're going to talk about the fundamentals of chemistry, talk about molecular building blocks in organisms, energy flow, and photosynthesis, and then talk about, um, the major hypotheses for life and then our knowledge of early life and how we got to be. So here we go. Um, so the one thing that I'll tell you that has impacted me growing up was one major thing was in 1989. Um, a a oil tanker called the Exxon Valdez was in Prince William Sound, which is the sound off of the coast of Alaska. Um, a captain of the boat was driving. He had turned his first mate in charge. He put his first mate in charge, went to sleep. Um, they ended up running the boat into a sandbar. And there's some question about his state of mind and um, where they were at. And they threw the boat into reverse and opened the hull up like a tin can. And they spilled nearly 12 million gallons of oil um, in Prince William Sound, and it was compounded because the sound is blocked on two sides, right? And so um, it really did make sure that oil um, was pushed into our land, in the water, everywhere. At the time, it was the largest oil spill in U.S. history. That's not so anymore with the Gulf Water Horizon incident in the Gulf of Mexico. Um, what came out of this? Um, in Prince William Sound and in the Gulf of Mexico, um, billions and billions and billions of dollars were affected, and tourism and money in remediation and bioremediation, which is pollution cleanup. And so uh, it was tragic for both events, lives lost. In Exxon Valdez, there was none. There were in the Gulf Water Horizon. And so um, even the tourism industry was majorly impacted, the fishing industry majorly impacted. And so bioremediation really is using biological methods to break down um, pollution and issues in areas. And what's interesting is we don't ever think about this, but um, oil is a natural product. It's made underground. It's a natural resource, and um, it does break down, and oil does get released naturally into the environment. That said, um, this and the Gulf Water Horizon were two great examples of what not to do right and what to do right. And we've learned a lot since then. Now, all oil tankers have double hulls, and so if one rips open, like in this case, which they only had one hull, um, now they have a protective hull to protect the other hull. Um, Basically, uh, we had to clean um, millions of feet of shoreline and water and rocks and birds and all sorts of animals in both cases. And um, you know, just when we think everything's going right, accidents happen, and we have to be prepared for that. Um, Chemistry is an amazing thing. I think about all of the contributions that we have had from chemistry. Um, If we think about impact wise, you know, global climate change, our climate change is affected by the things that we're doing, the gases that we're releasing. Um, uh, Acid rain's another good example. Our organisms are not the same as a result of things that we do, but they're constantly being impacted by the interaction of these chemicals. It is often said, and I have often said, that there's not a truly wild organism left on this planet. It's because we have water pollution, we have ozone depletion, we have energy issues, we have oil spills, we have acid rain, we have all of these things that we're contributing. Now, with that being said, chemistry also solves these problems. And we think about what chemistry is. Well, to understand that, we need to understand what everything is, right? So, matter. What's matter? Anything that takes up space and has mass. And matter can be transformed in one type or the other. And we think about what happens. Say I have a log. I put a log on my campfire to go make s'mores. As I do, the log then starts to burn. As it burns, it transforms into energy and light and gas and ash, what used to be a log, right? Now, if I theoretically could get all that stuff back and put it back, theoretically you could put it back into a log because it went into a log the first time. But we don't know how to do that. And the law of conservation of matter states that matter is neither created or destroyed, it's just changed into a new form. And so when we think about what makes those things up, fundamentally it's elements. Elements are the basic building blocks of all matter. And if you think about our periodic table has 120 elements on there. And an atom is the smallest unit of an element. And atoms are made up of protons, neutrons, electrons, and we can actually break them down even further than that to quarks and strings, which we won't talk about right now. But if you look at our periodic table is nothing but a great cheat sheet. It has all the information up there. And so the whole number that you see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc., is the atomic number. And that's actually telling you what the number of protons are. And in a neutral atom, protons equal electrons. So basically, this is telling you the protons and electrons of the atom. A proton is positive, a electron is negative, a neutron has no charge. So the electrons balance out the protons. And if we look at an atom, inside the nucleus is the middle. So protons and neutrons are in the nucleus, and the electrons are on the outside. And I'm not going to get into how many electrons can go into each shell, but it's real simple. 2 in the first, 8 in the second, 8 in the third, and then after that, we have 8 that go into each shell, but the ones in the middle jump up to the next level and get hidden. I don't really care that we go too far into that. But it's those electrons that are being either shared or borrowed that determine how our elements work together. If we have a different number of neutrons, so in other words, an atomic mass is the number that's like 15.9999, right? And so that's the atomic mass of the element. And remember, we always round up from 5. So if it's 15.999, it actually would round up to 16 as the atomic mass. Well, to take the atomic mass minus the atomic number gives us the number of neutrons. If we have the correct number of neutrons, it's a regular neutral atom. But sometimes we have more neutrons or less neutrons, which means it's heavier or lighter. And then we have a different mass number, right? And so then that becomes what we call an isotope. An isotope is an atom with a different number of neutrons, either positive or negative, right? Plus or minus, more or less, not positive or negative electricity-wise. And isotopes can be radioactive. And radioactive basically means they break down until they get to the right number of neutrons. We call that decay. Um, Once they become non-radioactive, they are a stable isotope. Now, to get through isotopes and understand reactivity or radioactivity, isotopes have what they call a half-life. A half-life is half the amount of time it takes for it to go and become stable. The deal is each time you get to a half-life, then you have another half-life and another half-life, and it has one of these curves that comes down and eventually gets to being stable. Um, Again, something like uranium has a half-life of 700 million years. We talk about, oh, well, is there a problem if we have radioactive dirt? Well, for us as humans and organisms now, yeah, that's a problem. But for the Earth, 700 million years from now, um, it'll all be okay. And so it's interesting to think about what that means. Some half lives are very quick, some all take a long time. So some are like a billionth of a second to billions and billions of years, right? All right, so we have atoms, we have elements. Now let's talk about molecules. When we combine two or more atoms of elements, it becomes a molecule. In this case, we have oxygen gas, which is a diatomic molecule. Di means two, atoms, atomic, come together. So oxygen gas, we can have things like C6H12O6, which is sugar, which means that we have 6 carbons, 12 hydrogens, 6 oxygens. They all come together and make the building block for us, our energy anyway. Water, H2O, carbon dioxide, CO2, right? And so when we talk about binding these elements together, whether it's either sharing or taking, so a covalent bond is where they share electrons, and an ionic bond is when they take them. Now, a polar covalent bond just simply says that one side is pulling harder on the other as far as the electrons are concerned, and we have a positive side and a negative side. Water is actually a polar covalent bond. If we talk about solutions, um, a solution basically is a mixture of substances that are liquid that can be separated. It's a mixture, right? So one of my favorite mixtures is cherry Kool-Aid, right? I can separate that. I just evaporate out the water, and the red dye number 5 and the sugar and all the other additives are left behind. Hydrogen bonds are really the reason why we exist, right? So we think about why they're looking for water on Mars and different planets and the moon and some of these other moons. They're looking for water because of hydrogen bonds. Why? Hydrogen bonds really do so many awesome things. One, they allow the absorption of heat in area is very stable. Another, life exists near water. And so it's this hydrogen, 2 hydrogens and an oxygen that create this opportunity for life. If we didn't have it, water would not be transported up trees if it weren't for the hydrogen bond and plants. We're not for the hydrogen bonds because they stick together. And so as they do through capillary action, they go up to the top of the plant. Water is a freak of nature in the sense that when frozen, it expands. When heated, it then releases that structure, but then when superheated, it expands again, which is a problem when it comes to our rising water conditions due to climate change and the melting of our glaciers and ice caps. So I'll explain. So when water freezes, it expands, it's less dense because it has a greater volume, it floats. If it didn't do that, think about what would happen. Ice would then get heavy, sink, sink, sink. Everything below the ice would die, perish. eventually our entire oceans, water, our lakes, rivers would be solid ice and nothing would be alive in there. And so, probably a pretty good thing, right? Um, when it dissolves, it then starts to move around and it becomes fluid. It travels over itself. And but then the problem is, additionally, when it gets hotter, it expands too. And so this is another reason why our coastlines are starting to flood quite a little bit. If we look at pH, pH is determined of the number of hydroxide, OH, and number of hydrogen ions that are in a liquid. And so when we talk about, or a substance, I should say, when we talk about pH, we have a scale from 0 to 14. 0 being extremely acidic and 14 being extremely basic. Um, Again, neutral being 7. And all it's doing is saying how many hydrogen or hydroxide ions we have. So if we have a hydrogen ion, we each time we move, it's a factor of 10. And so we can get a change in pH by either adding a base or an acid to increase either the more acidity or the basic it is. Organic compounds simply means that we're dealing with carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus. These are organic compounds. And organic compounds are the compounds of life. Um, Hydrocarbons are carbons that are only linked with hydrogen. Now, they're not always only linked because sometimes there's a molecule of sulfur and other things in there. But the hydrocarbons are basically what we talk about when we talk about petroleum based material. So it can be a liquid, a solid, or a gas. So methane, CH4, which is down here, it's a carbon with 4 hydrogens. Ethane, two carbons, and 6 hydrogens. Noted in the chemical formula down here, C2H6. Naphthalene, again, we can count this up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Sure enough, C10H8. I'll note also these lines here indicate single bonds or double bonds. This is a double bond. Okay. Polymer is a long chain or building block of life. And so when we talk about what these polymers are, these building blocks are, we talk about proteins, nucleic acids, carbohydrates. Those are the 3 essential polymers of life, right? So we've talked about those in biology before. Lipids are the fats and oils. They're not polymers, but they're extremely essential for life. If we look at protein, protein is in everything. If we have a problem with protein, protein basically is the building blocks for everything. It's what allows us to write DNA and RNA. It is used for everything. And we only think about it as the structural or the support, but protein really is so involved in making amino acids proteins make up amino acids, but so involved in all the functions of our body. And so they can speed up or slow down reactions. In the case of enzymes, they function with everything. Deoxyribonucleic acid or DNA and ribonucleic acid or RNA. This is how this is our genes. This is our hereditary information, and these different nucleotide sequences, which is the basic nucleotides are the basics of DNA and RNA. Adenine, cytosine, thymine, and guanine, and then you have uracil. These all get written into a code, and they tell our body what to do. Um, RNA basically is telling the amino acids to assemble into a specific form to create proteins. Genes, that tells what we should do functionally And so basically it determines what is going to happen at the cellular level. If we look at the genome, basically human genome is a sequence of genes that are written out and put onto chromosomes, and it tells us whether we have blue eyes and black hair or brown hair or whatever. A carbohydrate. Carbohydrates are pretty simple. They are carbon, hydrogen, and oxygen, CHO. When you find it, they are written CHO. C6H12O6, glucose, sugar, the basic building block of a carbohydrate. Um, you can get extremely large carbohydrate structures. They become starch. And so we think about a potato, which is starch, or a saltine cracker. If you put a saltine cracker in your mouth, actually just a regular cracker in your mouth, leave it there for a while, the enzymes in your mouth, which are proteins, start to break it down, and it will start to stay sweet because it breaks down into simple sugars. Lipids, again, fats and oils, they are very important. They don't dissolve in water. They're very important for function. They are energy. They are a support structure. Um, they keep things, the cell membranes together. They are steroids, right? So we hear that all the time. Now, we do have synthetic polymers. Those are plastics. Those are made from hydrocarbons. And there's all different kinds, nylon, Teflon, Kevlar, which is used in bulletproof vests. Um, but they are basically petroleum hydrocarbons. Um, a lot of times these cause problems because they are a long-lived, long-lasting molecule, and they cause pollution. And so environmentally, we do see a lot of issues as a result of this. If you look at our cell, um, the cell is the basic unit of life. And depending on whether you're prokaryotes or eukaryotes, a prokaryote is a single cellular organism. You are a eukaryote. And so you have organisms that have organelles, or you have cells that have organelles inside of them, um, whether it be the mitochondria or ribosomes or DNA. All of these different pieces make up a cell. And it's very important to understand that the mitochondria is where we get our energy from after we go through cellular respiration, the breaking down of our food into the building blocks or the molecules of energy for life. So if we look at how we're kind of organized, it's very easy to kind of figure it out. But we start at the atom, and then we go to the molecule, and then the macromolecule, and then an organelle. The organelles become cells, a bunch of organelles in the cell, tissue, organ system, and then the organism. And so we have a hierarchy. When we think about energy, um, we have two basic types: potential and kinetic energy. And then you've got this third one that's sitting there, which is chemical energy, which is in the bonds. So to be the energy is defined as the ability to change or do work. Um, and so potential energy, um, that would be like the water behind a dam. Kinetic energy, the water going over the dam. Chemical energy, the energy between bonds. And so when we eat our food, the food is potential energy. It goes through our body, and then it becomes kinetic energy because we use to make energy, heat, and we give off carbon dioxide and water. So it's C6H12O6 plus O2, that's the oxygen we breathe in, yields, that's what this arrow means, carbon dioxide, water, and then heat. First law of thermodynamics. Um, Energy can change, but it cannot be created or destroyed. And so, if we think about that, heat is given off into the environment, and as it does, the heat does not change. It just starts to warm other places or cool other places. And so, if we think about that and then think about the second law of thermodynamics, energy changes from a more ordered to a less ordered. Entropy is the word that describes what that means. It's kind of like your bedroom. You can clean it up and pick it up, but then all of a sudden you go from order to disorder, ultimately, right? And so you look at this wood here. You start it on fire. It gives off water. It gives off carbon dioxide. It gives off light. Gives off heat. We have ash. It then breaks down. Well, that stuff didn't just disappear. It changed into a form. Law of conservation of matter, law of conservation of energy, law of conservation of thermodynamics, same thing. That material is not created or destroyed, just changed into another form. We always have tried to harness energy for a quality of life, and we are getting better at it. Whether it's through electricity or steam or nuclear or kerosene, we've made energy the same way. We turn a turbine, whether it's a wind turbine, a water turbine, a kerosene, um, nuclear turbine, right? What's happening is we are turning a turbine through steam to create electricity. Um, and so when we think about how efficient something is, we look at how much energy output to the energy input, right? So energy conversion efficiency, the ratio of useful energy that you get out of what you put in, right? Um, sun's power, we get something like 2 terawatts of energy per centimeter every second of every day. I mean, we have so much sunlight that's striking the earth. It's crazy awesome. And so there's a big push to figure out how to harness that energy. The sun releases energy through what we call the electromagnetic spectrum, which is our visible light. Energy from the sun drives all the patterns on life on the earth. And so if you think about in the deep oceans, uh, we have this organism called a black smoker. A black smoker is a really cool organism down at the bottom of the ocean, and they feed on hydrogen sulfide. And there's a whole colony of crabs and different things down there. They're living off of these black smokers. And one would go, wait a minute, no sunlight reaches the bottom of the ocean. Well, you're right. But what causes our planet to have our hydrothermal vents and our volcanic activity on the Earth? Couple things. One, the sun, gravity, we're spinning, um, we're constantly, we have radioactive decay. And so it's kind of a stretch, but even the sunlight affects that down there as well. So let's talk about things that absorb energy from the sun through photosynthesis. Now, what you'll find with photosynthesis, the formula for photosynthesis is the exact reverse of that of cellular respiration. Those organisms are autotrophs. Autotrophs take in energy in the form of sunlight, they take in water, and they go and create sugar and oxygen as their byproducts. CO2 plus H2O yields C6H12O6 plus O2, right? And so it's the exact backward, here it is, right here. So this is done in the chloroplast through the light and the dark reaction and the Calvin cycle. And chlorophyll are absorbing the light energy, which causes the electron transport chain to get enacted. Don't care that you know that. And then it starts a chemical reaction, again, creating C6H12O6 plus O2. So when we think about what happens, then organisms use that energy that's been stored in C6H12O6 and O2, and we convert it to water and carbon dioxide. Those are heterotrophs. They feed on others. Autotroph means you are a self-feeder. Heterotroph means you feed on others. We are heterotrophs, right? And so we're getting that energy. Earlier, I talked about black smokers, hydrothermal vents. This is a chemoautotroph or chemosynthesis. Chemosynthesis using hydrogen sulfide to produce sugar. And basically what's happening is these black smokers are producing this hydrogen sulfide. These giant tube worms and crabs and everything like that are feeding upon the black smokers and the material coming out. These are chemoautotrophs. They are chemically feeding, chemically self-feeders, and it's a whole thing. But again, one would argue that without the sun, this wouldn't happen, right? So we're going to stop right here. I'm going to pick up where we left off. I want to say thank you so much for being awesome. I can't say thank you enough. You guys rock. Thank you for listening to this. I hope you get it. If you have questions, please see me. And thank you for making other people's lives better just because you're here. So we'll go ahead and stop.